How many people here are familiar with this concept of stationarity? Raise your hands. Yeah, it's a good number. For those who aren't, it's really not that complicated, it just sounds fancy. So it's very 20th century. So I'm going to start by talking about this idea of stationarity, this new 21st century idea of non-stationarity that's replacing it. Then I'm going to talk about how it applies to the quintessential wicked problem, I think, of the 21st century, climate change, a little bit. But I'm going to spend the bulk of my presentation talking about how it applies to another wicked problem, disruptive technologies and autonomous vehicles in particular. And I'll end by addressing this question again, how can geodesign help solve wicked 21st century problems? And when I use the term wicked, I'm using it in the Bostonian sense, wicked, extreme, wicked high tides, but also I'm using it to mean seemingly intractable problems that require really a paradigm shift to address Jack Kemp's proverbial Gordian knot. So let me start with this idea of stationarity versus non-stationarity. And there was a pretty influential article that came out actually in 2008 in Science magazine, which specifically addressed the idea of stationarity and water resource engineering practice. So this is a definition from that article. Stationarity is the idea that natural systems fluctuate within an unchanging envelope of variability. So again, they were talking about water resource engineering, and they were talking about design assumptions related to flood risk, water supply, that are no longer valid in an era of extreme weather and climate change. So an extension of this idea of stationarity is non-stationarity, which means that we can no longer rely on standard engineering parameters, standards, and the conventional infrastructure design solutions that result from them. So flash forward almost 10 years from when that article came out to the effects of Hurricane Harvey in 2017, which certainly reinforce or bear out this assertion that stationarity is dead. Now, I'll pose this question: how could our current engineering practices have protected Harris County and Houston, Texas from 8 trillion gallons or 24 million acre-feet of water, which is the total amount of water used in Southern California over nearly 6 years, falling on them during a 6-day period? And to underscore this point, the image on the right of the screen shows the maximum inundation forecast for Harvey, which NOAA used. They had a new water model they were testing before the event. So the areas in blue are the inundated areas that they were projecting in this extreme forecast. And as I understand it from folks at NOAA, it looked so extreme to them, they said, our model must be wrong. This can't be right. There must be something wrong with the model. But what actually happened is it turned out the rainfall amounts and effects during Harvey ended up being fairly close to this extreme prediction. And just another image over here. Anyone know what that image on my left is? It's a new weather phenomenon. It's not a nuclear bomb. It's called a rain bomb, exactly what it sounds like, an intense downpour of precipitation. And that image is taken over Phoenix, Arizona, of all places. So let me end with this segment with a couple of quotes. First from Paul Brown, who's a water resource consultant in California, and who first turned me on to this idea of stationary. So what Paul says is, because climate is changing, there's no way of telling how rare an event like Hurricane Harvey will be in the future. That's the essence of uncertainty resulting from non-stationarity. And again, to bear this out, Hurricane Harvey was the third so-called 500-year storm that Houston and Harris County had in 3 years. And the next quote is again from that article from Science magazine, in which the authors stated, we need to find ways to identify non-stationary probabilistic models of relevant environmental variables and use those models to optimize water systems. So geocoders take note. So I'm going to move on to the idea of what I asked as I was putting this presentation together. I asked myself, could we take this concept of stationarity versus non-stationary, which has been applied to natural systems, and apply it to a human system, say like new transportation technology? And as I looked into this, I actually found what scientists, statisticians say, stationarity is a totally human construct. It doesn't happen in nature, and I warned you I was going to get nerdy. So what they'll say is just look at the Big Bang theory of the universe, as the universe is by nature non-stationary. And there used to be a now discredited theory called the steady state theory of the universe, which said there was the universe has no beginning or end. And that's now thoroughly that's disproven, and the Big Bang is now the current paradigm. And just one other example I think is relevant to this audience is the idea of, I call it ecological steady state theory, succession to a climax community, which is like the ultimate in natural vegetative ecosystems. That's largely been replaced in contemporary ecological theory by the notion that natural ecosystems are in a continual state of flux due to disturbance. So yeah, why not? Let's take a look at autonomous vehicles and see how this idea of stationary versus non-stationary applies. So there was an excellent study that came out now several years ago, which is ancient history in the world of AVs, but I still like to quote from it. It's a study by Florida State University team led by Tim Chapin for the Florida Department of Transportation. And what they say, as you can see here, automated vehicles, their assertion, have the potential to transform transportation systems and land use patterns to a level not seen since the mass production of the private automobile roughly a century ago. Now that's quite an assertion. Just think what automobile mass production replaced, which was the age of horse-drawn vehicles, when the greatest transportation challenge was that cities were literally drowning in manure. No shit, this is true. There was actually something called the Great Horse Manure Crisis of 1894, when the Times of London predicted that within 50 years, every street in London would be buried under 9 feet of manure. Now that is like the essence of stationary thinking. So let's keep on this topic of stationary or steady state thinking, transportation systems. We design our transportation systems as if we're always going to be humans driving private automobiles. So, and we do that with what I'm calling here steady state transportation standards. So the first is vehicular levels of service. You know, how many roads have been widened, new roads built to try to improve our grade? Never works, right? And then the nirvana, free-flowing, open road, the American dream. What's happening? Where are all these cars coming? They're all getting in my way. You'll never get there. We're striving, but that's what's driving a lot of our transportation engineering practice. There are others, roadway classification systems, right-of-way design standards, and my pet peeve, minimum parking standards. That were come up with, some traffic engineer came up with them, that passed them down through generations. They're proliferated over and over again in zoning ordinances as if they're scripture. By the way, there aren't any traffic engineers in the audience, are there? Just checking, okay. So this whole idea of autonomous vehicles in an AV world, and I've been sort of observing this over the last 4 or 5 years, how the conversation has been evolving. And basically, there are kind of 2 visions that have been put out there. And the first one I'll call the utopian vision, which we're going to have shared vehicles, fewer cars, reduced congestion, cleaner air, our land use is going to be better. Oh, it's going to make things so much better. And then opposing this is the dystopian vision, privately owned vehicles, zero occupancy cars or zombie cars roaming the streets, more cars, more traffic, more pollution, more sprawl. Or in visual terms, heaven or hell. And this was my commute from LAX to Redlands on Monday afternoon. But obviously, you know, thinking about these things, it's not going to be one extreme or the other. It's going to be somewhere in the middle, which raises a question: how can geodesign help our communities move towards a utopian rather than a dystopian future? And by the way, I do need to give a shout out to Creighton Randall, the Shared Use Mobility Center, who is the source of these images and the slide about the utopian versus dystopian vision. So how this thing will turn out, whether it'll be a net positive or negative for society. And by the way, I'm not one who's in the Pollyannish camp. By no means do I think this is going to necessarily turn out really well unless we do something about it. But what's going to determine that will be the impacts of the technology. So these impacts are the primary or direct impacts and the secondary impacts. So primary impacts are ones that occur as a direct result of the new technology. Improved safety is the big one. I don't know how many, 40,000 people die a year. I forget the figure on the highways. Basically, that's the big #1 benefits that's being touted by it's a significant one by the industry. And there are individual benefits, convenience, productivity, so it's going to make it more fun to drive in cars again for people. So that's a benefit that accrues to the individual rather than the society. And by the way, vehicular emissions, which are the modern-day equivalent of horse manure, can be either a positive or a negative depending on how the vehicular fleet is powered, because virtually all projections when AVs are completely deployed is that there will be increased VMT, vehicle miles traveled. So secondary impacts from the new technology, these are the ones we designers, planners need to be most concerned with. So the flip side of that increase in individual convenience and productivity is the potential for increased sprawl as it becomes more easy and convenient, and you can do stuff while your car is driving you, so you can move further out to the hinterlands. The term sprawl on steroids has been used. Potentially decreased access or opportunity for underserved populations, including, really importantly, erosion of transit service for a transit-dependent population. We're already seeing this from Uber and Lyft, which are essentially AVs, but with drivers. Their goal is to get rid of those drivers eventually. So that's sort of a foreshadowing of the AV world. And there's another impact, obviously, which is impact on workforces, jobs in the trucking and vehicular transport industry. So there are a lot of things to be concerned about. And because we are concerned about the secondary impacts of the built environment, on the built environment and land use as we're planners and designers, I just wanted to cover a few points that are from that study from the Florida State University study from Chapin and his team. They found 6 overall impacts that could happen to the built environment as a result. And they're looking like 50 years in the future when AVs are totally deployed. So road design, AVs may create narrower and more efficient right-of-ways. So shrink those right-of-ways down, lane widths. Virtual infrastructure may replace physical signs and signals. Bikes and pedestrians. AVs could support or hinder the pedestrian experience. Big question mark there. Parking. AVs could affect the location design and demand for parking. A lot of projections that parking demand will go way down. Drop-offs. Drop-off areas will be a drop-off revolution, they call it, may replace on-site parking. And then redevelopment. This reduced parking may open redevelopment opportunities. And note that the authors are careful to say may or could rather than will, because probably even more so than climate change, it's uncertain now how this projected technological revolution will play out. So the key drivers in all of this, I think there are a few. The first and most important is whether we maintain our current model of privately owned automobiles or move in the direction of a shared fleet, which is the bet that companies like Waymo, Uber, a lot of the car companies are betting that we're going to move in that direction. So shared fleet versus privately owned vehicles. The second is whether that fleet is electric-powered, electric cars, or continues to be powered by fossil fuel. And then there's a third, I call it a wild card, which is the potential for declining, very much decreased cost of transportation resulting from AVs, and this notion that's referred to as mobility as a service or transportation as a service. It's generally believed that AVs will dramatically cut the cost of vehicular transport, eliminate the cost to the driver, and make more efficient use of the cars in service. Because right now, the average car spends 95% of its time parked, and they'll be used continually, at least that's the idea. So there are prognosticators who say that this reduced cost is actually going to drive consumer choice. So it's going to be so cheap and convenient to have an AVs rather than privately owned vehicles that will move in that direction. So where I think we need to go with this, and this is where they're getting back to the idea of geodesign, is scenario planning, which I think this is kind of the key to unlocking this. So I'm going to quickly go through a series of scenarios that were developed by Andres Sevstuk of Harvard GSD, and they have a project called the Future of Streets Project. And they, as you can see in this diagram, developed 24 scenarios based on basically 3 variables. Ones I've talked about: private ownership versus shared fleet, electric versus gasoline powered, and then level of automation from level 1 to human-driven to full automation. So this is Andres's characterization of the current automobility, what we have, which is basically privately owned vehicles driven by people with no automation and fossil fuel powered. So this diagram, out of the 24, this is the best case scenario. And again, this is when AVs are the predominant mode of transportation. So what you're seeing, it's a shared fleet, shared use, shared rides, electric powered, and full level 5 automation. And Andres had his team also illustrate what this might look like. So this is actually, I think, an illustration of Newbury Street in Boston. So they've got features like wide sidewalks with pedestrians, 2-way bike lanes separated but from narrow AV lanes, and designated pickup drop-off areas. Now here's the worst case scenario. Privately owned, fossil fuel powered, and level 4 automation, which allows for some human control. And here's the illustration of what that could look. So you've got narrow sidewalks, you've got AVs most of the street. You can't get across the street. There's pedestrian overpasses up above, no bikes transit in sight, and there's stalled AVs all along because there's no really designated pickoff areas, and I guess the people who are driving them don't know how to operate them or something. So anyway, that's the worst case scenario. Now, I'm going to close now with, well, first let me say, just to close that series, I showed the utopian versus dystopian visions, which is very broad and kind of, obviously broad brush and futuristic. What Andres is starting to do, his team, is looking, well, what does this really look like in reality? So they're going beyond that, and I think that's the direction we're moving in. And I'm going to close with a series of illustrations, actually, that were developed by our friend Tom Fisher, University of Minnesota, his team at the Minnesota Design Center. And they looked at, well, what could the positive outcomes of this AV revolution be? What could it look like on the ground? So here's one illustration: opportunity, more varied streetscapes. Did I skip over one? Opportunity, more varied streetscapes. Reduce urban heat island effect. More green infrastructure. I guess my slides got out of order, which is fine, but these are related. And opportunity for streets to become more people-serving public spaces. So again, these are a series of images, and there are more that they develop where they're trying to look at what it looks like now and how, for example, with green infrastructure, you could retrofit parking, pavement with multifunctional green stormwater infrastructure. So the question becomes, and I'm coming back to my original question I started with, how do we get there? How do we get from where we are to there? So at this point, I'm going to make a confession. We've got 1 minute. Ryan, I don't know why you let me up here, because I'm not a geodesign practitioner, so I'm not going to answer the question. I don't know the answer to this question, but I'm going to restate it in the form of a challenge to you, to the geodesign profession, to help our communities prepare for this new paradigm of autonomous mobility, and with it, by that extension, all the other wicked 21st century problems that we need to deal with, climate change, et cetera. So we don't know how this is going to play out over time, so how can you develop and model scenarios that's going to help communities make informed policy choices? Can these scenarios provide measures of the potential impacts of the choices on environmental, economic, and social goals? Can they be incorporated into real-time community engagement processes? And most importantly, will they lead to policy interventions that harness the potential of AVs to achieve community goals through new forms of regulation, incentives, pricing mechanisms, investments, design standards, and more? So, if I were a pessimist, I'd just say this in closing, I would say probably not. We're not going to get there. Just look what happened with automobiles and the secondary impacts. But I am a planner, so by nature I'm an optimist. So I'll just close by saying I'm hoping that we can embark on a journey together to find out if we can make this happen through geodesign. So with that, I will close. Thank you.